element has a unique atomic number? The modern periodic table is based on this property of elements. The atomic number of an element is the number of protons in its nucleus or the number of electrons in its energy shells. Atomic number is denoted by the letter Z, whereas the mass number of an element is the sum of the protons and neutrons present in its nucleus. Mass number is denoted by the letter A. If you take a close look at the periodic table, you will observe that for around 20 of the first elements, the atomic number and mass number are related. In the case of lighter elements, the mass number is approximately twice the atomic number. This can be observed in the case of elements with an even number of protons, such as helium and carbon. Exceptions are beryllium and argon. In the case of elements with an odd number of protons, such as lithium, boron and sodium, their mass number is twice the atomic number plus 1. Exceptions are nitrogen and hydrogen. The elements found in group 1A, namely lithium, sodium, potassium, rubidium, cesium and francium, are called alkali metals. All of them possess one valence electron in their outermost shell and share similar characteristics. Alkali metals are shining white solid metals, but are soft enough to be cut with a knife. They are good conductors of electricity. They are highly reactive and electropositive in nature. Along this group, atomic size, metallic character, and reactivity increases from lithium to francium. Whereas electronegativity, electron affinity, ionization energy decreases down the group. They are strong reducing agents and form electrovalent compounds with non-metals. The elements found in group 7A, namely fluorine, chlorine, bromine, iodine, and astatine, are called halogens. Astatine is the rarest element, so not much is known about it. Astatine does not have any stable isotope and has a very short half-life. The halogens possess 7 valence electrons in their outermost shell and share similar characteristics. The halogens are non-metals. They are bad conductors of electricity. Halogens are highly reactive and electronegative in nature. Along this group, atomic size, non-metallic character, reactivity, electronegativity, electron affinity, and ionization energy decreases down the group. The halogens are strong oxidizing agents and form electrovalent compounds with metals.
All of you know that gold, copper, and iron are metals. What about mercury and silicon? Are they metals or non-metals? Can you tell by just looking at them? Which element is more reactive, iron or copper? And if you are asked which atom is the biggest, aluminium, iron or copper, can you answer without referring to the values of their atomic sizes? Building up the periodic table has been a major scientific achievement. The broadest distinction in the table is between the metals that lie on the left-hand side and the non-metals placed in the top right region. The zigzag line separates the metals on the left from the non-metals on the right. These elements are called metalloids or semi-metals and show some properties of the metals and some that are more characteristic of the non-metal. Out of 94 naturally occurring elements, 70 can be classified as metal. Metals have 1, 2, or 3 valence electrons. Metals are electropositive in their nature. To achieve the nearest noble gas configuration, metals lose 1, 2, or 3 valence electrons while forming bonds. Hence, the valency or combining capacity increases as we move from left to right across a period within the metals. Non-metals are electronegative. The number of valence electrons in non-metals varies from 4 to 7. An atom of carbon has 4 valence electrons. Nitrogen has 5. There are 6 valence electrons in an atom of oxygen. And 7 valence electrons are present in an atom of fluorine. To achieve an octet, nonmetals need to share electrons or gain electrons. Nitrogen gains 3 electrons to attain an octet. The valency of nitrogen is -3. Oxygen needs only 2 more electrons to achieve an octet. The valency of oxygen is -2. And fluorine needs 1 electron to achieve stability. Hence, the valency of fluorine is -1. As we move across a period, the valency of nonmetals decreases from 4 to 1. How does the valency of elements vary in a group? Lithium, sodium, and potassium each have only one valence electron. To achieve an octet, atoms prefer to lose this single electron. Hence, the valency of elements in a group is constant. Is this trend seen in group 2 as well? Yes, all elements in group 2 prefer to lose the two valence shell electrons and form dipositive ions. As we go down a group, the valency of elements remains the same. The term atomic size refers to the radius of an atom. Let's take a look at the variations of atomic size. How does atomic size vary in a group? The atomic radius increases in spite of the increasing nuclear charge. Why? This is because the number of electron shells is also increasing. Let us compare the atomic radii of elements of group 1. Hydrogen has one shell occupied by a single electron. Its atomic radius is 37 picometers. Lithium belongs to the second period and has two electron shells. As a result, it has a greater atomic radius than hydrogen. The atoms of group 1 increase in size as successive electron shells are added. This trend is seen in all groups of the periodic table. As we go down the group, the number of electron shells gradually increases. The shells envelop one another like the layers in an onion. As a result, the atomic radius increases despite increasing nuclear charge. How does the atomic radius change from left to right in a period? Consider elements of period 2. The atomic size decreases as we move from left to right across a period. Is this trend seen in period 3 too? Yes. As we move across a period, there is an increase in the nuclear charge. This pulls the electrons closer to the nucleus. Therefore, the sodium atom's radius is larger than the magnesium atom's. In period 4, a potassium atom has a radius larger than a calcium atom's. In a similar fashion, the alkaline earth metals in group 2 are smaller than their respective neighbors, the alkali metals in group 1. Sodium, with atomic number 11, has a single valence electron in the third shell. The atomic number of magnesium is 12. The nuclear charge also increases by 1. This causes the attractive forces between the nucleus and the electrons to strengthen. This effect is counteracted by the increasing number of electrons, but the increased nuclear charge is the stronger factor. Thus, the atomic radius is reduced. To sum up, in the period table, the atomic radius decreases from left to right along a period. Metallic character is the tendency to lose electrons, and the non-metallic character is the tendency to gain electrons during bonding. Metals tend to lose electrons when forming bonds. That is, they are electropositive in nature. Down the group, the effective nuclear charge experienced by valence electrons decreases because the outermost electrons are further away from the nucleus. Therefore, metallic character increases down a group. Across a period, as the effective nuclear charge acting on the valence shell electrons increases, the tendency to lose electrons decreases. Hence, metallic character decreases across a period. Unlike metals, which are electropositive, the non-metals are electronegative. Electronegativity is the tendency of an atom in a molecule to attract the electrons of a bonding pair toward itself. This quality depends upon the size of the atom, the number of valence electrons, and the effective nuclear charge. Moving across a period, the atomic radii of the elements decrease, but their electronegativity increases. The number of valence electrons increases from 1 in sodium to 2 in magnesium, 3 in aluminium, 4 in silicon, 5 in phosphorus, 6 in sulfur, and 7 in chlorine. Electronegativity increases with an increase in the number of valence electrons. Electronegativity also increases with the increase in effective nuclear charge. Does the electronegativity increase as we move across a period? This graph reflects the trend in electronegativity across period 3. Most of you must have played the game, tug of war. The stronger player pulls the rope towards him and wins. This tug of war game is played at the atomic scale also. The rules, however, are quite different in the atomic world. Today, we shall explore some of them. Consider a bond between two atoms, A and B. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Remember, the element that pulls the electron pair towards itself is more electronegative. The attraction between a bonding pair of electrons and the nucleus depends on the number of protons in the nucleus, the distance from the nucleus, the number of electrons between the outer electrons and the nucleus. This chart shows changes in electronegativity across period 3. The electronegativity increases across a period. Why does electronegativity increase across a period? Let us understand this by taking the example of two elements from period 3, sodium at the beginning and chlorine towards the end. Think of sodium chloride as if it were covalently bonded. The valence electrons in both sodium and chlorine are in the third shell or M shell. The sodium nucleus has 11 protons, while the chlorine nucleus has 6 more protons in its nucleus. Due to this, the bonded electron pair gets pulled towards chlorine to such an extent that sodium and chloride ions are formed. This chart shows the patterns of electronegativity in groups 1 and 17. Observe that the electronegativity decreases down a group in the periodic table. To understand this trend, let us take the examples of hydrogen fluoride and hydrogen chloride. In the case of fluorine, the bonding electron pair is closer to the nucleus, and the attraction is therefore high. In the case of chlorine, the bonding electron pair is further away from the nucleus, and the attraction is lower. Fluorine is therefore more electronegative than chlorine. In the periodic table, fluorine is the most electronegative element, and cesium is the least electronegative. Since electronegativity must always increase towards fluorine, it becomes easy to remember the patterns of electronegativity in the periodic table. Electronegativity is related to ionization energy. The ionization energy is the energy required to completely remove an electron from a gaseous atom or ion. Just like electronegativity, ionization energy also increases across a period and decreases down a group. When you like something, you have an affinity for it. On the atomic scale too, we find that positively charged nuclei have greater affinity for electrons. Electron affinity reflects the ability of an atom to accept an electron. It is the energy change that occurs when an electron is added to a gaseous atom. The stronger the attraction, the more energy is released in the process. Electron affinities are concerned with the formation of negative ions. In the periodic table, electron affinity increases from left to right across the period and decreases as we move down a group. Let us try to understand this trend. As we go down the group, the number of electron shells gradually increases. As a result, the atomic radius increases despite increasing nuclear charge. Owing to this, the incoming electron experiences a lesser pull from the nucleus. The lesser the attraction, the lower is the electron affinity. Electron affinity increases from left to right across the period because of a decrease in atomic size and the increase in nuclear charge. This causes the incoming electron to experience a greater pull from the nucleus, thus giving a higher electron affinity. The electron affinity of atoms with completely filled shells is almost zero. An atom does not accept an electron in its outermost shell if it already has a stable configuration. Modern periodic law is the consequence of the periodic variation in electronic configuration which determines the properties of elements. The properties of the elements depend on atomic number and electronic configuration. In a period, elements are arranged in increasing order of atomic number. The maximum number of elements in each period is determined on the basis of quantum numbers and the order of filling up of orbitals. Elements with similar properties are arranged in vertical columns called groups or families. Elements in a group have similar outer electronic configurations in their atoms. Hence, the modern periodic table is sometimes also known as Bohr's periodic table. Lanthanum and 15 elements constitute the lanthanide series, which resemble each other as the differentiating electron is entering into the 4f orbital of the anti-penultimate shell. They exhibit the variable oxidation state, and all of them are metals. Similarly, the 15 elements following actinium, in which the 5f orbital is filled, are called actinoids. Electronic configuration is the arrangement of electrons into orbitals around the nucleus of an atom. There is a direct relationship between the position of an element in the periodic table and its electronic configuration. In the modern periodic table, the elements are arranged in vertical columns called groups and horizontal rows called periods, based on increasing order of atomic number. There are 7 periods in the modern periodic table. Each period indicates the value of the principal quantum number n of the valence shell. The first period corresponds to the filling up of electrons in the first energy shell, or K shell. For n equals 1, there is only one s orbital, which can accommodate only 2 electrons. Therefore, the first period has only 2 elements, namely hydrogen and helium. As the outer shell is completely filled in He, it is chemically unreactive and placed in the 18th group along with the other noble gases. The general electronic configuration of the first period is 1s12. The second period corresponds to the filling up of the electrons in the second energy shell, n equals 2 or L shell. This shell has 4 orbitals, namely 1 2s and 3 2p. As each orbital can accommodate 2 electrons, the second period contains 8 elements. The general electronic configuration of the elements in the second period is 2s12, 2p1 6. In a similar way, the third period corresponds to the filling up of the electrons in the third shell or M shell. The third shell has 9 orbitals, 1 3s, 3 3p and 5 3d. As we move from sodium to argon, s and p orbitals of third shells are being filled up progressively. Fourth period, there are 18 elements in total, in which part of the fourth shell and part of the third shell are being filled up. As we move across the fourth and fifth periods, it has been observed that the outermost and penultimate energy shells are filled up with electrons. In potassium and calcium, electrons enter into a 4s orbital as it is lower in energy than 3d orbitals. From scandium to zinc, the 5 3d orbitals are progressively occupied. From gallium to krypton, 4p orbitals are being filled up, as 4p orbitals are higher in energy than 3d orbitals. In these elements, the outermost and penultimate energy shells are incomplete. In the fifth period, 1 5s, 5 4d, and 3 5p orbitals are being filled up with electrons. In the sixth and seventh period elements, the last 3 energy shells are incomplete and begin with the filling of the sixth and seventh shells respectively. Out of the 32 elements of the sixth and seventh periods, the first 2 electrons enter the s orbital, 1 the d orbital, the next 14 electrons occupy f orbitals. The next 9 enter d orbitals, and the remaining 6 electrons fill up p orbitals. There are 18 groups in the periodic table. In a group, all the elements have a similar outer shell configuration. In the first group, the s orbital of the outer shell is filled up with 1 electron. All the elements in the second group have 2 electrons in the s orbital of the valence shell. In 3 to 12 groups, the d orbital of penultimate shell gets filled up. Group 13 elements are known as boron family. Group 14 elements are called as carbon family. Group 15 elements which resemble nitrogen are represented as nitrogen family. Chalcogens and halogens have highly negative electron gain enthalpies and readily add 1 or 2 electrons to attain the stable noble gas configuration. Noble gases are chemically unreactive as their outer shells are completely filled. In groups 13 to 18, the p orbitals of the valence shell get filled up with electrons. The elements are classified into 4 blocks: S, P, D, and F blocks, based upon the orbital that received the last electron. The S block elements involve the filling of the outermost S orbital. S block elements are highly reactive as they have low ionization energies. Their compounds are predominantly ionic. The p block elements have valence electrons in p orbitals of the outermost shell. Most of these elements are non-metals and metalloids and are called main group elements. S and p block elements together, known as representative elements, are highly reactive. In D block are elements belonging to 3 to 12 groups in which the d orbitals of the penultimate shell are being filled up. They are transition metals as they transit the properties from the most electropositive S block to the most electronegative p block elements. Two rows of elements at the bottom of the periodic table are called F block elements, as the last electron added to each element is filled in the F orbital. %78% of the available elements are metals. Metals are solids with high melting and boiling points. They are malleable. They can be fabricated into thin sheets. They are ductile. They can be drawn into thin wires. Cu is used in making electrical wires and tungsten is used in making filaments as they are good conductors of heat and electricity. Where do we find the metals in the periodic table? Non-metals are soft and brittle. Except Br2, most of them are gases or solids. They have low melting and boiling points. They are non-malleable and non-ductile. They are poor conductors of heat and electricity. Graphite is an exception. Metals and non-metals in the periodic table are separated by a set of elements which behave like metals and non-metals, called metalloids.